What does it mean to be a solution?
Like two things together.
Good. Two things together. Typically in what state of matter? A solution is typically, typically liquid, right? Typically liquid. So solutions are homogeneous mixtures, okay? Any sort of homogeneous mixture. So could be non-liquid, but typically solutions are liquid mixtures. Homogeneous means it is the same throughout the entire sample. So if I were to pull a sample from the top and pull a sample from the bottom of my container, they would be the same. Okay. Usually it is a solid that's been dissolved in a liquid, things like salt water, sugar water, right? Those types of things would be considered solutions. Cleaning materials, all that kind of stuff. Makeups, lotions, all of these types of things would be examples of solution. Right? They are the same throughout. We can see liquids dissolve in one another, and when we say they dissolve in one another, it's just a really basically tight mixture, right? They are interwoven so closely that we call them dissolved, and so that's really what we're looking at. Gases could be dissolved in liquids. I think carbonation is the best example that we see of that in common use, right? We see carbonated beverages in which the bubbles are hopefully evenly dispersed throughout that substance, and so that would be considered a gas dissolved in a liquid. We don't see it super often, okay? But those are all examples of solutions. So the two terms that we should know are solvent and solute. Solvent is the one in larger quantity, okay? It's the one that is doing the dissolving, and then the substance that is being dissolved is called the solute. So typically the solute is the solid thing, right? It's the powder, it's the sugar, it's the salt, it's whatever's going into that liquid to be dissolved. Sometimes I do a demo of making a solution, but I think that's something we've seen before. Can you at least tell me what type of glassware we use to make solution? Do you remember what type of glassware specifically we should use when we're going to make a solution? Like what type of glassware from the lab should we use? Okay, not an Erlenmeyer flask, it's a different name, different type of flask.
Isn't it the one that's like really long that has like the big thing?
That's right. That's right. Okay, yes, you're kind of mixing and matching, but you're close. An Erlenmeyer flask looks like this.
Oh, I was thinking the one with the circle.
Right, this one is what we use to make a solution. It looks something like this. This is called a volumetric flask. Okay, a volumetric flask. And the only difference is that an Erlenmeyer flask really doesn't have any or very many indicative markings on it for measurements. The volumetric flask, however, has one singular marking up here on the neck that would represent its volume. So we only use volumetric flasks to measure a single volume. This might say that it's 100 milliliter volumetric flask, which means we make our solution, and if we go over that line, we have to do it again. We have to start all the way over, because if we overshoot it, now our concentration is not what we say it is, because our volume is too great, right? So when you make these volumetric flasks, they are measured extremely precisely to that single measurement and then nothing else. Okay, because we can't figure out where half of that is, right? I don't know where half of that is. So you can't make 50 mils by just filling it up halfway. It doesn't work like that. So volumetric flasks are used to make solutions because they're very precise to that one particular measurement. And it's got this any idea why this skinny neck here instead of just like a beaker, right, with different measurement lines? Any thoughts about that? Why such a skinny neck here on a measurement where we need to get a really precise volume?
Because it's easier to read.
It is easier to read, and in a skinny neck, the water tends to make that meniscus more visible, right? On a wide mouth container, the water just looks flat, right? It's hard to kind of tell where that meniscus is. But the skinnier the container, the more the water molecules stick to the sides of that container, right? And we really see that meniscus form, so we're able to measure exactly at that meniscus. When we make a solution in that volumetric flask, you'll be able to see that pretty clearly, right? The skinny neck allows us to see that meniscus really well. Okay, but that's what it's called, a volumetric flask. Volumetric. This one was called an Erlenmeyer flask. Okay, and it is mostly meant for stirring because it just has a nice motion for stirring. Okay, so which one is the solute here? Yeah, the Kool-Aid, right? And water would be the solvent. We call water the universal solvent. And that's not really fair because it's not really universal. There's not, every single thing doesn't dissolve in water, right? We know that. So there are certain compounds that don't dissolve in water, but water is a good solvent for things that are polar. Okay, water is a polar molecule. Would we agree with that? Do you kind of remember what polarity means? A little bit. So here's water. Water has polar bonds, which means that these electrons are being pulled toward oxygen. So here is our polarity for our bonds. Okay, hydrogen has a partial positive, oxygen has a partial negative. Partial positive, partial negative, right? We've got this formation of polarity happening in our molecule. So in general, my molecule is polar. Now, water is a really, really, really polar molecule. It helps dissolve other polar molecules, okay? Other ionic compounds, it helps dissolve those because this partial negative pulls on the partial positive of that molecule, whatever it is, and envelops it, and now the water molecules surround that new thing. So if I was going to look at sodium chloride, for example, we're going to see the positive side of this water molecule get pulled to the oxygen, right? And then another water molecule will come attach itself, right? And so it kind of breaks that down, all due to the polarity of water. Now, what about molecules that are nonpolar? Well, they do really well dissolving in nonpolar solvents. Okay, we use the little saying, like dissolves like. Like dissolves like. And all that means is that substances like themselves dissolve better with substances like themselves. I kind of said that funny. Substances dissolve better with other things like themselves. So polar dissolves in polar, nonpolar dissolves in nonpolar. Okay, so you can kind of tell when something is polar or nonpolar just based on whether it dissolves in water. That's an indicator. Okay, all right, I already talked about all of this. Sorry, I skipped ahead a compound, but you can fill in what you need to, but we kind of talked through all of that. Okay. Anything that is considered aqueous means that it has been dissolved in water. So when we see a compound in a chemical reaction that says this, that means that this substance has been dissolved in water. And it means water is not affecting the reaction at all. It's just the place for it to happen. So you can have aqueous solutions and as a part of a chemical reaction and water not be a product or a reactant in that particular reaction. So it can take place in water, but water's just allowing it to happen, right? It's not actually changing. The identity of water is not changing. Okay, I do actually want to watch this little video here. I need to pull it up on my computer because it won't work on the iPad, but I want to watch this video of the process of dissolving so we can kind of see a couple ways that we can encourage our solute to dissolve. So thinking about what we just talked about on the molecular level and those water molecules insulating it from having, think about what do we need to happen to speed up the dissolving process, the picking off of those particles. Any thoughts? Stirring is a good one. Good. Why does stirring work?
Because you're breaking up all the particles.
Good. We could be physically breaking up those particles. We're also encouraging more collisions between the water molecules and the other molecules, right? So if they collide, they're likely to stick together. But if they don't collide, if everything's just sitting, right, there's less likelihood. Okay, so stirring is one. What was the other one we said?
Heat.
Heat is a good one. What's another? Why does heat matter on the molecular level? I agree. You're right with heat. Do you know why? When you heat.
Oh, because there's more energy.
That's right. That's right.
That's
right. When we add energy, those particles will move faster. Again, encouraging collisions on the molecular level. So when they start to move faster, that's exactly what will happen. Not only will the water particles move faster, the salt particles will move fast enough that their bonds will start to break, which then increases the surface area for water to come in and pluck it off. Right?
Is that like the same when they like heat up like steel and big metals? Like the bonds start to break so they can like form it into things.
Yep.
Can you add more solvent to it to dissolve it?
Yeah, that's a good question. That's a good thought too. Yeah, I could dilute it, right? That's what the word is that we would want to call that. But I could water it down, right? That would increase the likelihood of water causing that collision. Yep, good. Also think about, it could be physical manipulation before it even goes in, right? So you have rather than put in a big chunk of sugar, right? A giant sugar cube, we pour in granular sugar. Right, and because those granulars, right, they're already broken apart. I think about it when you make. Have you ever made like frozen orange juice? You know, from the can. You guys ever made that stuff?
Yeah.
Okay, that like you can buy like frozen concentrate
And
orange
you
juice.
pop the top off.
That's right. It's like it looks like a little old, like a biscuit container, you know, but you pour it in orange juice. You never made it before? Okay, yeah, I grew up making that. I feel like, but it's hard to find now. Believe it or not. So it's just basically like frozen orange juice concentrate. So that means we literally have to water it down for it to become the right consistency for orange juice. But it's not only solid, it's solid and frozen. And so that takes a lot of manipulation to get it incorporated and get it dissolved. But that is another one. You could cut that into smaller pieces, and that would encourage the dissolving process to go faster. But yes, heat and stirring and physical manipulation are the three ways that come to mind. And then watering it down, that was a good one.
This might not have anything to do with it, but why?
Solubility values. They have a solubility number assigned to them. And solubility is just the amount of substance that can dissolve in a certain solvent. So typically our solubility is given in how many grams of solute can can dissolve in 100 grams of solvent or in 100 mils of water. So it might have a solubility value of 34 grams per 100 mils, right? That would tell us that 34 grams of my solute, whatever it might be, could dissolve in 100 milliliters of water. And that would be what we call saturated. Okay, saturated means we're at like our ideal level of concentration. We can reach what we call super saturated. That would be when we have too much solute to solvent ratio. Right? Does that make sense? That's kind of like our Kool-Aid example, right? When our sugar gets too heavy and it falls out. And then you have, I don't remember if they call it undersaturated or unsaturated maybe. That's like where our solute to solvent ratio is too high on the solvent side, right? We've got too much liquid in there. All of them work, but it's just kind of a range of acceptable or ideal values. Okay. I'm going to move past how things dissolve well in others, and we've kind of looked at that in the past. We just need to kind of understand how temperature might affect things. Temperature typically increases a solubility value. It increases the likelihood of dissolving. Okay, like we talked about earlier, if we want to heat it up, that'll help us move things faster through the dissolving process. Gases on the opposite side of that actually do worse with heat. Okay, gases actually do worse with heat. They decrease, their solubility decreases with temperature. The most common example I can think of is, let's say you leave your soda in the car on a hot day and you come back and what happened?
It's like flat.
It's flat, right? That heat and that pressure cause those gas particles basically to get squeezed out of the liquid. Mm-hmm. And so now they're all at the top of your container and you open it, all gone, right? And now you've got a hot, flat pop.
So you just have to shake it up.
Yeah, you could shake it up. Yeah, you could try to shake it up. And you might get it a little bit, but most of those particles have been squeezed out of that liquid, right? The pressure has caused those gas particles to.
When you put like an open pop like in the fridge, the carbonation like goes away a little bit. Does it go out into like
it goes into the fridge, yeah.
The fridge.
Yeah, it's all carbonated. Yeah, it gets it dissipates too quickly, right? Yeah. Because once it's opened, now that gas really doesn't have any pressure that's keeping it in that in that liquid. That's why like pop is sealed so well, right? And that's why like fountain drinks, they're not carbonated until the last second.
They're so good. That's why they're so much better.
Yeah.
These are like fresh.
They're like fresh, right? Because it comes in as a syrup and the carbonation, and it just combines at the last second. And so that's why it doesn't last very long, because it just it doesn't stay very long at room temperature. But yeah, an interesting question. This just kind of talks about, okay, we already said like dissolves like. Sorry, I'm kind of skipping all over the place here. Yep, we talked about this. Greater contact between solvent and solute molecules means faster dissolving. Good, we dove into all of that already. Very good. All right, let's get into concentration. I know we covered this in Honors Chem last year. Leia, do you remember covering this in regular Chem? Did we do like molarity?
I think
Moles per liter? I kind of think we did, maybe just a little bit. So part of this section will still be review, and then we'll get into what's called net ionic equations later, which will be a little different and all that kind of stuff. But let's review a little bit of molarity. Molarity is how we measure concentration. Do you know what I mean when I say concentration? Like, does that word seem familiar to you, right? When I say how concentrated it is, it's how much stuff is in there, right? How dense our solute is. Yeah, that's a good one. Good way to use it, okay? So molarity is given with a capital M, and it's moles per liter. I like molarity. It's fairly simple, right? Fairly straightforward, but molarity is big M, and we just measure in moles of our solute over liters of total solution. That's kind of an important part. It's liters of total solution. So when we say total solution, that means the volume of not only our solvent, but also the volume of our solute. So even the little volume that increases when I pour that in, it's going to raise my volume a little bit. So it's volume of total solution, not just liters of water or whatever. Okay, so let's try this one. A sugar cube is dissolved in a teacup that holds 350 mils of water. What is the molarity of the solution? So it gives us the formula here for sugar, and our original value is given to us in grams. So what has to be done first? Right, we're going to convert from grams to moles. So grams to moles. I'm not going to write that whole formula out because I don't want to, but we do need to find the molar mass of that sugar molecule. Do you guys have your periodic tables out? Can you grab those for me? I had fairly large,
I had
270, good, that's what I had as well, okay. So 270 times 4 gives me 1,000, no.
Oh, I was about to say this.
Silly me, okay, no, I did it. I was like, that doesn't seem right. Okay, this feels better. All right, so moles, how about 0.0148? I don't really care where you round that. Not a huge deal one way or the other, but there's our moles divided by our liters. This is given to us in milliliters. So how can I convert that? Divide by 1,000. So 350 would be 0.35 liters. I shouldn't have deleted my calculator here, but I did. 0.35. And that gives me a concentration of 0.042 molar. We just give that with a capital M. That is both our variable and our unit. Yep. Both variable and unit. So we are able to, when we say that unit, we just say it has a concentration of 0.042 molar. That's how it's written and how it is said. Okay, so molar. Coming back to us a little bit?
Yes.
Okay. Why don't you try this one on your own? And then we'll dive into a little more complicated one here in a second. Okay. Now it's going to ask us for volume. How many liters of a 3.4 molar isopropanol solution can be made with 78 grams of isopropanol? So We're given our concentration this time, 3.4 molar equals moles over liters. We're going to convert that first. 78 grams. C3H8O, so do you remember our shortcut here?
Just divide 1.3 over 3.4.
That's right. We're going to switch these two spots, right? Anytime our unknown is in the denominator. We use this type of equation for density. We use it for molarity. We use it for a lot of different things here, but anytime my variable's on the bottom, I'm going to say liters equals 1.3 moles over 3.4 molar and get about 0.382 liters.
So that's the same as multiplying both sides by liters and then dividing.
Exactly. We're just doing this shortcut. So let's walk through the algebra just a second. So I would multiply by L, multiply by L. So now I've canceled. And so now I'm left with L times 3.4 equals 1.3. So now I divide by 3.4, divide by 3.4. Right now this is gone. It leaves me with L equals this over this, right? Yep. So we've done the algebra, but now we're able to do it quicker. Yep. Okay, very good. All right. How many grams of potassium phosphate would be needed to make a 1.32 molar solution in a container holding 4.2 liters? Okay, this is a really common type of actual lab application question, right? I have to make solutions for our stuff all the time. And I've only got so big containers and I only wanted so much of a concentration, and so I'm having to make it. So this is really applicable, but 1.32 molar is equal to moles over 4.2 liters. Do we have to do any fancy math here, or is this just straight multiplying?
It's just straight.
This is just straight multiplying because I want moles by itself in the numerator. It's already in the numerator, and so I don't have to do anything differently with that.
So you don't have to find the...
Sorry, we are still going to find grams. Yes, I just meant for the moles part, but yes, you're right. So I came up with like 5.544 moles. Okay, and we got to know what potassium phosphate's formula is because we're going to have to find grams. So we need to know what its formula is.
K3PO4.
Good, that's what I have also. K3PO4. So we'll go moles to grams of K3PO4. 39 times 3 plus 31 plus 16 times, okay, 60. 212 maybe?
That's what I have.
Okay, perfect. All right, so in order to make this compound, I need 1,174.5 grams. That's a lot. That's a lot. But you're making a lot of substance, and the actual compound itself weighs a lot, right? A mole of salt weighs 58.5 grams, right? So if you think about that, this has a mass 4 times that essentially. And so it might not look like a huge pile of it because it's a denser compound, right? But you're also making over 4 liters. So you got over 2 jugs, right? And I'm thinking of a 2-liter container here. I've got over 2 of those. So it is what it is. Yep. Okay. All right, let's look now at how can we find the concentration of single ions in our compounds. Okay, I want to make sure I want to do this today, which I think I do. Okay, yes. So we can use molarity to calculate concentration of individual ions. Let's first identify some ratios of individual ions, okay? Give the concentration of each ion in the following solution. So let's say I have a solution that is 0.5 molar cobalt 2 nitrate. Okay, there's my formula. And my overall solution has a concentration of 0.5 molar. Now, I want you to think about this question here. Within this compound, how many, if I have one molecule of cobalt nitrate, how many cobalt atoms are present?
Or one.
Just one, right? Because this is just a one. How many nitrate molecules are present? 2. Okay, so let's break that down. For every one molecule of cobalt 2 nitrate, there is 1 cobalt and 2 nitrates. So if I have 10 of those molecules, how many cobalts do I have? 10. And how many nitrates do I have? 20, right, because the ratio is 2 to 1. So now that everything else applies exactly the same. My concentration of individual cobalt ions, since it's a 1 ratio, is just equal to 0.5 molar. But what would the concentration of my nitrate ions be? Exactly, it would be 1.0 molar. It would be twice the concentration of my full thing. Because you got to think about, if the container stays the same, it stays in its container, and all of those ions split, and now they become their own thing. For every split molecule, you would have 1 cobalt and 2 nitrates. And so now the concentration of nitrate in comparison to cobalt has to be twice as much, right? There are 2 nitrates present for every cobalt. So does that kind of make sense? We're looking at just at the ratio of it, okay? Okay. The easiest way to do it is to find the concentration of your full molecule, and then you can break it into its parts and pieces just based on the ratio there. Okay?
2 on the end of it. That's why it's double.
That's right.
Okay.
That's right. This house is about to die. Okay. I think that's the E.
So because of that.
So give the concentration of each ion in the following solution. This is iron 3 perchlorate. So let's talk about what ions will it break into.
Iron and purple.
Good. And what would iron's charge be?
Oh, it's the Roman numeral.
Right. It would have a Roman numeral. So look at it. It would be here FeClO4 3. So if I reverse the crisscross,
So it'd be the
it'd be plus 3. And then we would have ClO4, and its charge would be minus 1. And how many of this molecule would there be?
3.
There would be 3 of them. Okay, so this would be like times 3. Okay, so if this concentration of my total compound is 1.0 molar, what is the concentration of my iron atoms? 1.0 molar. And what is the concentration of my perchlorate ions? 3 molar. Yep. So it seems bizarre that, like, how can one thing be more concentrated than the other within a single solution? And it's just all about the ratios, right? There are 3 times as many perchlorate ions as there are iron ions. So that's just literally what concentration is. How many are there per gram of water or liter of water or whatever it is? So it's all about the ratios. All right, this says calculate the number of moles of chloride ions in 1.75 liters of 1 times 10 to the negative third molar zinc chloride. So we want the number of moles of chloride ions. But before we do anything, let's kind of write out what we do have. We know the concentration is 1 times 10 to the negative third. I hate working in scientific notation, so I'm just going to make it that. Right? It's the same, but I don't want to be in scientific notation. And this is ZnCl2. Now, there's a couple different pathways we could follow to find our our final answer. What you could do is find the number of moles of zinc chloride and then multiply it by 2 because I'd have twice as many moles of individual chloride ions because of that ratio. That's one way we could do it. Or I can just look at the full concentration and say, I know chloride's concentration has to be twice that much. Would we agree? So we could do it that way too, right? If you kind of forget about the ratio system, we could go ahead and solve for moles and then look at it being twice that much. But I'm going to go ahead and do it this way first. I'm going to solve for concentration of chloride must be what? 0.002 molar of Cl minus. So that's still molar. It's not moles. It's still molar. And so then I can do moles of chloride over 1.75 liters. Right? 2 pathways, and we're doing the same work. We're just doing them in different order. So really, whatever way you want to do it is completely fine. Okay, so I would take 1.75 times 0.00. And I get 0.0035 moles of Cl minus.